what I want to say is what a person like me, who is a philosopher of science, but also a lover of science and a connoisseur of science, sees in a project like CREDO. And what I thought when I heard first about CREDO is that this is an example of science, the type of science that I love most. So I'd like to present to you these two basic types of observational campaigns that I do see happening in science. This is just two end members, as we say, so it's not a classification, it's more like a spectrum. And the first, the type A, would be the kind of project that we usually hear about in the media, meaning big-scale project aimed at a very specific phenomenon. Usually you produce something special to observe it. You spend a lot of money. I don't mention money over here, but it's obvious. So projects such as all of the microwave background radiation observations, yes, Kobe, Planck, etc. Many things in particle physics, such as the CERN and all the colliders. So something built specifically to study better a very narrowly defined phenomenon, a phenomenon that is known already. So this would be type A. And type B would be a completely different way of doing science. First of all, using cheap or existing equipment, not building something special. And CREDO is a beautiful example because we use smartphones that people have in their pockets. So this is the observational equipment. It's cheap. You didn't have to spend $1 for your tens of thousands of data points, right? People give it to you. So you didn't have to go to your boss and say, I need $1 billion for my equipment. No, the equipment, other people bought it for $50, right? So a cheap way of getting data, which comes at a price, meaning you have to observe something which is relatively easy to observe, which is available, which is right there. Because, I mean, by definition, you don't get extremely specific, specialized equipment lying around and being cheap. But what I think is very special about type B observational campaigns is that they have a very high probability of finding completely new phenomena. And I'm going to show you, I was planning on discussing 3 case studies, but I'm going to discuss 2 because time is precious. And one will be remotely related to astronomy, because I'm going to talk about meteorites. And the second has nothing to do with astronomy, because I'm going to talk about biology. But I hope to show you what I mean by type B research. Now, this is a meteorite. This is a chondrite. So if anybody knows meteoritics, it's the type of meteorites, that are remnants of the oldest materials in the solar system, and they are studied extensively. But there is one study which I just love. It's a study from 2007 of people who just know chondrites from all possible angles. And what you usually do is you study this specific objects in a chondrite. You can see them because these are the special things. You see the red blobs? They are called chondrules. And they are the most exciting objects in the chondrites. And they said, no, we've studied them already, we're not going to study them. And there are other objects, CAIs, amoeboid, olivine aggregates, and a whole list of interesting things. But what they did is they said, okay, we're going to study the least interesting bit of the chondrite, the place where nobody looked, but it's just everywhere, the chondrite matrix. So they zoomed in on this bit, and they noticed a couple of interesting crystals, and they said, well, I think you can guess what they said. Okay, so let's zoom in on the part where there is nothing. And they zoomed in, and they found quite a lot of interesting things. We're not going to go through them, but I'm going to tell you what kind of things can you expect when you look at the place that's easily available. You don't have to find something special. You just that's the whole point of the study, is that you study the place that everybody saw before, but nobody thought it's going to be so interesting. It's just a bland, neutral place. And they wrote an article with a very poetic title, A Cornucopia of Pre-Solar and Early Solar System Materials. So what they found was a large number of kind of unexpected tiny crystals. Some of them, by the way, some of them diamonds. So this might be the answer to your riddle. I mean, there are diamonds older than the solar system in solar system materials, and it's produced in supernovae. So they found a lot of interesting things. And one lesson that's kind of important for philosopher of science is that when you do this type of study, so when you focus on this massive thing, which is the chondrite matrix, and you just look for anything, that's the whole point. You look for anything, you have to concentrate on the places you wouldn't normally look. And in this case, for instance, there's this little place. As you can see, this picture is made in 3 filters: lithium, silicon, and magnesium. Lithium in red. You see this little dot over here? So in the whole area that they studied, there was one little place, it was actually 1 pixel, that was extremely high in lithium. Now, lithium is not a very common element. So a normal person studying a normal meteorite for normal reasons would say noise, probably noise. I mean, 1 pixel of super high lithium, I mean, it's not interesting. I have work to do, right? But somebody noticed that in the very same spot there's chromium, extremely high amounts of chromium. So they zoomed in on the bit and they found a very unusual mineral. In fact, basically a new type of mineral, lithium chromide, which doesn't really occur in nature that much. It's a very rare element. It's a very rare chemical, lithium chromide, in mineral form. So they found at least 1 new mineral. They found a lot of other different things. But what they did, and I think this is kind of interesting, is they approached it with an open mind. They didn't approach it with specific questions, such as, what is the size of the chondrules, what is the size of this, what is the... No, they just kind of looked at it and asked the question, okay, what can I find interesting? With a completely open mind. And they wrote a perfect article. And the second example I want to discuss is from biology. I'm going to talk about single-celled organisms. So before there were animals, there were protozoans, my favorite types of organisms. And there's a class called diplonemids. Diplonemia is the name of the class. That they are usually called diplonemids by people who talk about them, which is about 50 people in the world. And so it's a small group. It's a small group of protozoans. At the moment, there's between 10 and 15 known species of diplonemids. And so this is the phylogenetic tree, so the genealogical tree of certain protozoans that shows the species of diplonemids and 2 closely related groups. This is Euglena. You probably know Euglena. It's the green thing in lakes, in ponds, sometimes in puddles, when there is a warm summer day and you see a puddle, muddy puddle, and it's greenish, it's probably this fella. It's, a single-celled alga, right? And this causes disease. It's a kinetoplastid. So, okay, so this is the standard genealogical tree of diplonemids. Okay, interesting. Well, not very much. But what they did, and this is not an invention of one group, this is something that we do for about 20, 30 years now. We're doing it better and better. It's called environmental sequencing. And it's a beautiful idea. Because usually what you do in biology, and this is again a type A kind of thinking, is I'm interested in an organism, so I capture it, I culture it, I watch it, I sequence it. So I have a very specific research program. I'm going to study this very organism, and I do whatever I can to study it. I cut it into pieces, I freeze it, and so on and so on. So this is an intensive program aimed at something we know to learn more about it. Now, what environmental sequencing is, it's pure type B science. Because what you do is you travel to a whole bunch of places. You can choose them randomly. You can just spin the globe, close your eyes, and point to some place, and you go there, it's usually an ocean, and you take a bucket of water, or you take a bucket of mud, or you take a bucket of sludge from some place. And what you do is you make a list of all the DNA that you found in the sample. So basically what you do is, okay, so I wonder what type of organisms could live in this bucket of water. So I make no assumptions about them other than they have DNA, which is, I mean, it's true of all life. Now, it's not that easy as it sounds because you kind of have to start by something. So when a group of people, Lara et al., in 2009, they did a big study picking up water from whole different places all over the globe, and they were looking for relatives of diplonemids. Now what they did, and I'm gonna, it's the phylogenetic tree that they got. I'm gonna color it just for you so that you see the same color that was here. Now these are the known species, yeah? These are sequences that they found, and these are the two groups. So it seems that in the between these two groups and these two, there's like a whole bunch of organisms. So at the moment, we know nothing about them other than we have their DNA, but the method is very cruel because you take the water and you drain it with, you get anything that's not water and then you blend it. You make a big sludge of, protoplasm, right? And you sequence all the DNA. So all the organisms are long dead, but we know that they are there because we sequenced them. So now there's like, oh, okay, so there's a lot of organisms, but it's just the beginning because there's actually more of them. If you take a look at those two little groups, in fact, this is the size of the groups. So here, squeezed at the top, you have a couple of the known species, 5 or 10 species, and each of those could be a new species. It's kind of like, the size of the revolution is, we know 10 species of great apes or something like this, 10 to 15, humans, chimpanzees, gorillas, orangutans, that. So let's say that's, I don't know, 10 to 15 species. Now imagine that someone with one study discovered 150 more of them. I mean, it's something like this, yeah? Except that this is diplonemids. So this is not that exciting. But the thing is that this is being done all over biology, especially with single-celled organisms. So once more, the method is that I pick up a bucket of water and I'm looking for something. But the interesting thing is that it's not that easy because you have to zoom in on the organisms that you're looking for. So what you usually do, you take a little bit of the DNA of this thing and this thing, and you're looking for something similar. So then you get this. So then you take a little bit of this DNA, and then you get these. So you take a little bit of this DNA, and then you get those. And this is an interesting procedure, because you are venturing into the land of the unknown using little bits of information of what you know. So it's a very interesting method. It's kind of like, we know now that there's an ocean of unknown species and groups and phyla. I mean, we are only starting to learn the true diversity of life on Earth. But the method is, it's very difficult to find something. You don't know what it looks like, you don't know how it behaves, you don't know nothing about it, but you know it's there. It's very difficult. So what the biologists do is they start with something like they know, but they allow for a little change, for a little elbow room. And they find something quite kind of similar but strange. But then they take this and this and this. So it's a very interesting method. And the further example, I'm not going to go through this a lot because time is precious. I wanted to talk about a study in sociology or maybe economics. There was a big study of the behavior of people who use the London Underground. And if anybody went to London and used the tube, I mean, it's very confusing. It's very difficult to understand because there's so many ways in which you can travel through London. It's extremely confusing. And to make the long story short, these people studied a whole bunch of different patterns. Where do you start? Where do you end? The problem is there's like millions of data points. So the same problem. We have a lot of data, but how to find patterns? So they found an interesting thing that after a strike, there was a 2-day strike, people started using the tube differently because some of the stations were closed, so people were forced to use the tube in a different way for 2 days. and they found better routes, which is kind of cool because, so for 2 days, a bunch of stations were closed, so people had to go using different stations, and about 5% of people in London found a quicker way to get to their work. So these people estimate that it's economically, it's an economically good thing to mess with people from time to time, because if you force them to be creative, they will, and they will find a better way to travel, and it's going to be cheaper for everybody. But the third case was something like, so this is a story of finding a needle in a haystack, because they had millions and millions of data points. Everything is registered using Oyster cards, so everything is electronic registered, about how to find data. So it's a kind of different story. So from the 3 examples that I gave, I think it's worth remembering that each of these examples give you a certain lesson. The first one, that you have to analyze the noise, because if you're very careful, there's no noise. I mean, each signal gives you some information. For example, it can tell you how bad your detectors are, because if your detector 1 times in 10 gives you a spike just on itself, then it's information about your detector. I mean, every single bit of information was created by some process. It may be noise in the cables, it may be problem with the detector, but you have to know it, right? So the problem with type B things, if you don't know what you're looking for, it's very easy to to find something and you don't know if it's noise, if it's not noise. The little grain in the meteorite, I think it's a perfect example. The second, start with the known to find the unknown. So you take the method of little steps. So I can imagine it being used in astrophysics. I didn't prepare any examples from astrophysics, but this is being done. I mean, you watch a whole lot of gamma ray bursts, for example, and you have all the different types of flares and novae that you watch the curves, and there are so many types of the curves. The classifications capture about 50–60% of all cases, so you don't know what the others really are. So instead of zooming in on the 15% if you analyze all of them, you have the problem of what they really are. So going step by step from what you know to find variations is a way to penetrate the unknown. And the third, well, you may need a lot of data to find a signal. And the case of Oyster cars and Metro, I think, shows it greatly. So when I prepared it, I really thought that CREDO is more type B science, but I'm not really that sure anymore, and I would be very interested to talk about it if you find it interesting. So thank you very much for your attention, and let's talk.
Thank you very much. Questions? Robert.
Okay, at the beginning you told us about cheap projects, which finally can lead to very sophisticated, very good products. A good example is, I don't know, Apple or Macintosh, made by a few people, 2 or 3, working at the beginning in garage, without money, without anything. They just had a passion, and they were a little bit crazy, like these guys think here. This is very good for the project. But more seriously saying about projects or ideas which need money, this is the problem, because if we apply for money for given project, we have to specify, we have to prove that we know exactly what we want to get finally, and that we have to prove that we exactly know how to achieve it. So there is no freedom, no space for random looking like kids do, and finally they found the best way.
Yeah, exactly. That's exactly the point of the distinction, because when you do a big project that has a very specifically set goal, it's a different situation. You can say, okay, I need $1 billion, but there is this very important constant of nature, and I'm going to give you 3 more decimal digits, right? So this is a very clear situation. If I collide these 2 particles with an energy that's 2 orders of magnitude higher, I'm going to estimate the electron mass with 3 additional digits. So I spend a lot of money, I build specialized equipment, and I'm studying what I know to know it a little better. Yeah. But I have to tell them what I'm going to need the money for. I have to give them a scenario. You're going to learn this, exactly this, yeah? But the beauty of type B experiments, I think, is that you don't have to do it because you don't have to spend that much money because you're using what you have. In all those cases, this is the exciting thing. They used generic off-the-shelf equipment. They just went to the shop, you know, one equipment, please, yeah? I'm going to spend it from my pocket and I'm going to ask for reimbursement later. But the thing is that if you study, you know, a big area that nobody's really looked at before, just open-minded looking for a phenomenon, then you can find something really new, right?
Other questions? Okay, I can have mine. So, thank you very much again. And speaking about types, I think we are not forced to be only type B. So we already now discuss scenarios for billions of dollars, but we do not necessarily need it at the beginning. So we start the easiest steps first. So the easiest step is off-the-shelf solution, exactly as you said. Although ultimately we do not want to limit ourselves to smartphones only. Our strategy is open to actually any type of detectors, including super professional neutrino detectors or gravitational wave sensors or cosmic ray arrays and so on and so on. But okay, step by step. But in a sense, we are type A and B together. We will choose what we like more.
That's the best strategy, right?
Another thing. I mean, you mentioned analyzing the noise, and if you are careful enough, there is no noise, and that's actually very, very true. Also, in some other sense, slightly different. So we would love already now analyze noise of other experiments. For us, it's a signal. So, for instance, we've had hackathon yesterday on analyzing astronomical data, astronomical dark frame data, which are made by covering astronomical CCDs to identify hot pixels. And when the CAM is covered, okay, with a few consecutive frames, but pixels are identified, but during the same time, cosmic ray tracks are seen. So this is noise. Happily, luckily, they do not throw it away. They store it, it's public, and we want to bite it. So our noise, right, but also other noises are fine with us.
One man's noise is another man's signal, right?
Okay, I see no other questions. Thank you very much once again.
Thank you.